want to thank Angie for inviting me to participate in this. And let me start with a confession. Calculus, I think, is the toughest nut to crack in collegiate education. And I always thought I was a person of courage, but I've never lectured. But the calculus is the last place that I ever took the plunge that I should have taken 30 years ago. And Ted Behavior is to blame for that. When Ted and I began to collaborate and I saw some things that he was doing, I said, basically, why not? So here we go. I do want to emphasize, there's way too much curriculum for a semester in every calculus course, whether it's calculus 1, 2, or 3. So part of my remarks are, unless I go belly up on what I intend to say, are about ways to buy time in order to give the chance for the mathematics the students have a chance for the mathematics to fester so they can do some stuff themselves. Okay. All right, here's our standard, your standard curricular context: limits, derivatives, integrals, and applications. And questions that I always ask myself, what would they be exposed to, and what's the foundation, if I can build from it, I'll have a chance to get them to make the mathematics. Now, where I've taught, it's quite likely that a student in your first year calculus course will have already had calculus. And those who have not had calculus will be intimidated by the ones that have. Calculus is much, much more difficult to teach now than it was in the early 80s when the numbers were skewed the other way. Because the ones that had calculus ended up just getting blown away by the ones that hadn't, because they tried to rely on what they already knew as opposed to getting involved with the ideas. And it would always, first test, second test, third test, fourth test. But it's not that easy now, because the students that haven't had it are intimidated just by the numbers. So, let us pause here to entertain some possible social challenges, because in Calculus 1, possible means nearly certain. Every client discipline thinks they can teach calculus better than you can, so they're going to get, you're going to get sniped at from your client disciplines. But then again, calculus to them means the student can knee-jerk a response when the model comes up in their discipline that they want to use the calculus on. From colleagues in mathematics, save rigor for the majors. You might not give it one crack at a math student. If they're going to develop the habit of mind, you got to have it happen when they're under your care. From the students, you got the second tier, at least at James Madison, you got the second tier of the testably able students that are coming in. They're really ones that really killed the BC test or started calculus 2 or calculus 3. But these are the people that did calculus in high school and did enough on our placement tests so that they were good high school students. And they didn't get that way through rigor, which is what college mathematics is all about, at least in my opinion. And so they likely got that way by being really good pattern matches. You've got to empathize with this. They got no reason to trust you. I mean, what do you know? I was good. My high school teachers told me I was good. I am good. Why should I desert something that's tried and true just on the possibility that you might be right? So you have to empathize that they have a good case. But we can't give in. We've got to find a way to take what we know we're working with is at least good ability of some type and channel their enthusiasm for what they do well now into something that they can do that will allow them to grow intellectually. So, the transition is from this is right because the back of the book says so, or this is right because you say so, to this is right and here's why. And you know when you won when the student says, this is right and here's why. Now, I want to show it to you real quickly. Here's the dictionary. I wasn't bluffing, this is quick, but I'm coming back to it. But what I want to emphasize is that even if I put this in 12-point font, it fits on 5 pages. There are 21 words. Now that can give a glimmer of hope to anyone. What other course have you ever taken that someone only asked you to master 21 words? All right, now, here's the course plan. I want to build a theory. It's about rigor. So what is my theory going to be about? It's not entirely rhetorical. Here's what it's going to be about. It's going to be about the list. And there are the elementary functions that, unless your calculus book is completely atypical, any function in the book can be written or either spliced from sums, products, and or compositions of functions in the list. So we're going to produce a function for the list. But since all the functions in the book are sums, products, and compositions of functions in the list, our first rigorous point of attention is the algebra of functions. Well, if you're going to do the algebra of functions, it's pretty darn important if, again, you're going to make language the basis of your attack on the mathematics, that we be able to say carefully what it means to be a function. So we can talk about adding them, so we can talk about multiplying them, and so we can talk about composing them. The core vocabulary from the theory of sets that I want them to use, and I fight the battle if it needs to be fought in terms of their familiarity or willingness to use the word set, element, order, pair, first coordinate, second coordinate. Definition 1 is a number function. Definition 2 is a domain of a number function. Definition 3 is the range of a number function. And you notice I've carefully made my standard presentation of definition to be preconditions, and here's the word. Preconditions give you a platform for problems. Validate the preconditions so the mathematics can be applied. And in trying to diagnose where the students in my care can launch from, I can make any pre-calculus problem I want to appear with the list or domain or range by asking questions about domain and range. Definition 4, composition. This is the one that to your students, it's a substitution principle. They've never articulated it as mathematics. It's a substitution principle. So composition is the place where you get a chance for the student to actually say what they mean in a place where always before they've just substituted. I mean, that's the word that covers everything associated with composition. You'll notice that I've also specified the notation that goes along with these. One thing that students who don't succeed with me can still tell their friends, Dr. Parker says, make notation your slave, not your master. The notation comes last. All right, so here's the definition of the algebra. So the other part of the theory that I want my class to develop, a theory for the list and a theory for the algebra. Okay. So the first unit is involved, I can use this to diagnose where their pre-calculus is by getting them to establish, notice that I've made a very careful precondition that you can't add them unless they have the same domain. Gives me a chance to distinguish between a number and the range being added with number addition and adding two functions, which has very stringent preconditions. The precondition on composition that insisted that the range of the right composite be a subset of the domain of the left composite is a rich place for homework problems. So through this, I get a distinction between number algebra and function algebra, a platform for asking the question to give me a chance to see how to put in place what they're going to need skill-wise. The other thing is that if you happen to be inflicted with early transcendentals, as we were in James Madison over the past 6 years, this usually having to do exponential and logarithm as a part of the list, and together with the algebra to make those two functions meaningful, or to find out if they have any reason to think they're meaningful, this actually makes the first unit in the course. There's no calculus in it. On the other hand, if you're not doing early transcendental and this goes smoothly, you can launch right into approximation. The way I flesh out the first unit is I give them the introductory experience in modeling, where we go all over the book, read applications, make models from number functions, and then say what's the question, but we don't have the mathematics tool to answer the questions. That means when you come back to them later, all that's left is the mathematics. Second unit on limits, I emphasize, I do the limit unit on approximation rather than what is the limit. The structure that I need here, I put interval in there just for contrast because I used the extreme value theorem as an axiom. I need that structure anyway. Number 8, segments my approximator. Number 10, I would insist that the number be close to the domain as a precondition for limit. You'll notice I do not have the standard definition for limit because I insist, if the localizing condition for the limit's actually in the domain, if I'm formalizing approximation, by golly, if I nailed the thing, I don't want to throw it away. So it gives a nice place to go with. The textbook's definition is slightly different than ours. Can you find what's going on, what's different? But this way, continuous functions, you already know what the answer is before you start. And if you're talking about approximation, that's a good thing. So then, the homework problems are all about making estimates because that's what the definition of limit has formalized. Tell me how close you want to get. I'll tell you how close to get to the localizing condition, and by telling you what the set of neighbors is, and what you have to validate is, yes, indeed, what the function pairs each one of those is in the domain with is close enough. So you can design that problem in 5, 6, 7 ways, and then you turn them loose on the list to prove the limit theorems. And they'll get lines. Somebody will get lines. Somebody will probably get squares. Somebody will probably get square root. Somebody will probably, but there again, if they don't, you can ask the right questions about numerical examples and they'll get them, and then you've got a theory of limits for the list. The sum theorem, the product theorem, the composition theorem. Somebody usually gets the sum theorem. You can lead a class through a proof of the product theorem. But the nice thing is at the end, for any given example, give me epsilon if I know the proof. Here's a segment that works. Why do I know it worked? I proved it works. So the theory is to pay off. You see, we've made a case that the proof is more powerful than the statement of the theorem. For the derivative unit, I choose to generalize slope. Notice that I give a name to the Newton quotient so that I can write the limit of a function rather than the limit of a range of a number in the range of the function with an animated first coordinate with an arrow stuck in front of it. Once again, it's a chance to make the distinction between a number range and the function itself. And there's the derivative. And now, in this context, the slope approximation function, they can do all but sine and exponentials themselves because a number algebra in the range of the slope approximation function gets you to the theory you developed in the first unit. So you get to do what is the limit, what is the limit, what is the limit, and you get a theory for the list for derivatives. And one real nice opportunity is that the first pass at sine doesn't get the theorem they were expecting. it gives you if zeros in the domain of derivatives of both sine and cosine, then it has a derivative everywhere. That's a really, really nice lesson for differential equations. And if you're doing early transcendentals, the algebra is much simpler in exponentials. Very briefly here, modeling the area problem is the integral unit, and I used the Eudoxus principle as the geometric basis for a single lecture with lots of pictures, and then try to get the class involved in validating that this structure actually captures what the geometry suggests we need. The integrals defined for continuous functions. And one of the things about buying time in making approximations for integrals before you get the fundamental theorem, that's a great place for max optimization problems because you're getting estimates that are proved to be on either side. So after the fundamental theorem is proven, you now have the stage to go back and revisit whatever models you want to make. I typically split that into models in mathematics so that I can get them after things like the mean value theorem, depending on time, length of a graph, but all the standard max mins. Then the models that they've begun to work on in the first unit, now you're in a position to do the mathematics. So a chance to emphasize that applied mathematics is made by interpreting some version of reality within mathematics and then using the certainty or the validation of proof to be able to say the mathematics is right and then try to take it back. And so the fourth unit becomes an application unit with anti-differentiation driven by the fundamental theorem of calculus being an application of your derivative theory, and the stage is set for calculus 2. Just in the 10 seconds I no longer have, here are a couple of support documents for, first off, why set of ordered pairs, answer, to be able to take number functions where the coordinates might not have squat to do with geometry to analytic geometry. It's a good place to make the case for careful articulation. And here's an introductory modeling assignment. There. Either that or such an absurd concept that nobody would be willing to try.
Thank you very much.